Hi, welcome to Sunil Maths tutorial, class number functional analysis, class number 20. In this video, we prove a theorem. Let us see. Capital B and B dash are two Banach spaces, and capital T maps B into B dash is a continuous linear transformation of B onto B dash. Then the image of each open sphere centered at origin in capital B, centered at origin in capital B, contains another open sphere centered in B dash. So right, let us prove this theorem. Lengthiest one, be patient and follow carefully. Let capital B and B dash be any two Banach spaces, and capital T maps B into B dash, capital T maps B into B dash is a continuous linear transformation and is itself onto also. Now define let two open spheres. Let SR be the open sphere. Let SR be the open sphere with radius small r, centered at origin in capital B, and SR dash, same SR dash be another open sphere, SR dash be the open sphere with radius small r, centered at origin in B dash, respectively. Remember that I defined two open spheres, SR with radius r with centered at origin in B, SR dash with radius r centered at origin in B dash. Remember that both are open spheres with same radius r. Both are centered at origin, but one is defined in B, the second one is defined in B dash. Right. Now we see that. What is SR? Let us write the definition of open sphere. X such that X belongs to B and norm X is less than small r, which is equals to X such that X belongs to B, norm X by R is less than 1. Now replace X by Ry. Ry such that Y belongs to capital B, norm Ry divided by R is less than 1. It can be written as which is equals to set of elements Ry where Y belongs to capital B and R into norm Y divided by R is less than 1. This is nothing but set of all elements Ry such that Y belongs to capital B and norm Y is less than 1. So this R is constant. It can write outside of the set small r into Y such that Y belongs to B, comma norm Y is less than 1. So this by applying, if you understand the set carefully, this is also an open sphere. Centered at origin with radius less than 1. What it means? This set can be equivalent to small r into S1. Because radius is 1. So now you observe that SR is equivalent to R into S1. So we prove that SR is equals to R into S1. Now apply T of SR. T of SR is equals to T of R into S1. Capital T is a linear transformation. So it can be written as R into T of S1. R into T of S1. Therefore, T of SR is equals to R into T of S1. Remember this equation. Throughout the theorem, it is useful for us. Let it be equation number 1. Let it be equation number 1. Now we show that, or now it is sufficient, it is sufficient to show that T of S1, T of S1 contains, T of S1 contains some SR. T of S1 contains some SR. Then obviously the open sphere lies in another open sphere. So we go for it. First we prove that First we prove that T of S1 bar contains an open sphere. T of S1 bar contains an open sphere SR dash. So right, for each positive integer n belongs to capital N, consider an open sphere Sn in capital B. Let us see. For each positive integer small n belongs to capital N, consider an open sphere Sn in the Banach space capital B. Then it is clear that this B can be written as union n is equals to 1 to infinity Sn. Union n is equals to 1 to infinity Sn. Since capital T is onto, by applying the definition of onto, B dash is equals to T of B. It is equals to T of union n is equals to 1 to infinity Sn, which is equals to union n is equals to 1 to infinity T of Sn. Let it be equation number 2. Therefore, this is B dash is equals to union n is equals to 1 to infinity T of Sn. Again, since this B dash is complete, we know that every Banach space is complete. So B dash is complete. Now by applying Bayer's theorem, I write here. Therefore, Bayer's theorem. What is the Bayer's theorem? I write the statement here. If a complete metric space is the union of sequence of its subsets, then the closure of at least one set in that sequence must have non-empty interior. Remember that this is known as Bayer's theorem. You remember that. You practice this theorem, you by heart this statement. Bayer's theorem states that if a complete metric space is the union of sequence of its subsets, then the closure of at least one set in that sequence must have non-empty interior. Here B dash is also union of subsets, union of sequence of its subsets. So by applying this Bayer's theorem to our B dash, there exists some T of Sn naught has an interior has an interior point y naught, has an interior point y naught, which may be assumed to lie in T of Sn naught. That is, y naught belongs to T of Sn naught. Y naught belongs to T of Sn naught. Now consider a mapping. Consider a mapping f that maps from b dash into b dash such that f of y is equals to y minus y naught. Let us consider a mapping that maps from b dash into b dash such that f of y is equals to y minus y naught. We can see that this f is a homeomorphism. We can see that this f is a homeomorphism. This f is a homeomorphism. By using this mapping, we see that by using this mapping f, 0 is an interior point. 0 is an interior point of the set capital T of Sn naught bar minus y naught. Because already it is a y naught is an interior point of T of Sn naught. So obviously 0 is an interior point of T of Sn naught minus y naught. So T of 0 is an interior point of this one means there exists an open set. There exists an open set capital G such that y naught belongs to G and it is subset to T of Sn naught bar. There exists an open set G such that y naught belongs to G. It is subset to T of Sn naught bar. Y naught is subset to, applying the same condition to our theorem, f of y naught is belongs to f of G subset to f of T of Sn naught bar. So here in the first case we write only y naught belongs to G subset to T of Sn naught bar. Here in this case I write the images. F instead of y naught, f of y naught. Instead of G, f of G is subset to f of T of Sn naught bar. So right. Therefore, which implies as this condition implies as y naught minus y naught is equals to 0, which belongs to f of G, and this f of G is subset to T of Sn naught minus y naught bar. So this condition implies as 0 belongs to f of G, which is subset to T of Sn naught bar minus y naught. This shows us 0 is interior point. 0 is interior point of T of Sn naught bar minus y naught. Again, we know that in the initial stage, y naught is an element in T of Sn naught. In the first Bayer's theorem, we conclude that y naught belongs to T of Sn naught. So y naught is an element in T of Sn naught. Now applying the same property, T of Sn naught minus y naught is subset or equivalent to T of S2n naught, which implies T of Sn naught bar minus y naught is subset to T of S2n naught. Let us take an element y belongs to T of Sn naught minus y naught. Then there exists another element x belongs to S2n naught such that y is equals to T of x minus y naught where norm x is less than n naught. Also since y naught belongs to T of Sn naught implies there exists an element x naught belongs to Sn naught such that y naught is equals to T of x naught because T is onto with the property norm x naught is less than or less than n naught. Norm x naught is less than n naught. So right, we continue. So Using all these calculations, we conclude that y is equals to t of x minus t of x naught. This is equals to t of x minus t of x naught. This is equals to, by linear transformation definition, t of x minus x naught. Let it be. Therefore, we conclude that y is equals to t of x minus x naught, where both x comma x naught belongs to Sn naught. Let it be equation number 3. Equation number 3. Here norm x is less than n naught. Norm x naught is also less than n naught. Applying these two conditions, norm x minus x naught is less than or equals to norm x plus norm x naught, which is less than or equals to n naught plus n naught, which is less than or equals to 2n naught. Therefore, norm x minus x naught is less than or equals to 2n naught. This condition implies as the element x minus x naught belongs to S2n naught. S2n naught. If the element x minus x naught belongs to S2n naught, then T of x minus x naught belongs to T of S2n naught, which implies T of x minus x naught is nothing but y that belongs to T of S2n naught. Already we defined here. Here see, from equation 3, y is equals to T of x minus x naught. So T of x minus x naught belongs to T of S2n naught means y belongs to T of S2n naught. So this shows us y belongs to T of Sn naught minus y naught. So which implies sorry which implies T of Sn naught minus y naught is subset to T of S2n naught. T of S2n naught. That is the point. T of Sn naught minus y naught is subset to T of S2n naught. So right, already we proved that in the initial stage, T of SR is equals to R into T of S1. R into T of S1. Applying the same logic, here T of S2n naught is equals to 2n naught T of S1. 2n naught T of S1. Applying the same property here, you can write like this. T of Sn naught minus y naught, T of Sn naught minus y naught is subset to T of S2n naught, which is clearly subset to 2n naught T of S1. Let it be equation number 4. Again, since this f is a homeomorphism, this f is a homeomorphism which is both continuous one onto and open mapping homeomorphism, then f of T of Sn naught bar is equals to f of T of Sn naught whole bar. Oh, because of f of a bar is equals to f of a whole bar by applying this axiom. So this condition implies as T of Sn naught bar minus y naught is equals to T of Sn naught minus y naught whole bar, which is subset to 2n naught T of S1 bar. Let it be equation number 5. But origin O is an interior point. But remember that this origin O is an interior point. Origin O is an interior point of T of Sn naught minus y naught. This condition implies as origin is an interior point. Origin is an interior point of 2n naught T of S1. Tn naught T of S1. So origin is an interior point of 2n naught and S1 means clearly this origin is an interior point. This origin is an interior point of T of S1. T of S1. Hence there exists an open sphere. Hence there exists an open sphere of radius epsilon. Hence there exists an open sphere of radius epsilon greater than 0 centered at origin. in centered at origin in B dash, centered at origin in B dash, in B dash, contained, contained in T of S1 bar, contained in T of S1 bar, contained in T of S1 bar, which implies as S epsilon dash is subset to T of S1 bar. S epsilon dash is subset to T of S1 bar. Let it be equation number 1. Now complete the proof by showing that. We complete the proof. We complete the proof by showing. We complete the proof by showing that. By showing that S epsilon dash is subset. S epsilon dash is subset or equivalent to T of S1. Remember that. So finally, if we show that this one, there must be an open sphere in B dash containing, there must be an open sphere in B dash containing an open sphere in B. So remember that. Remember that. So to complete this proof, which is to complete this proof, let us take an element. Let us take an element y. Let y be an arbitrary, let y be an arbitrary point of S epsilon dash such that norm y is less than epsilon. We take an element y which is arbitrarily chosen from an open sphere S epsilon dash with the property norm y is less than epsilon. Since S epsilon dash is subset or equivalent to T of S1 bar, which implies as y belongs to T of S1 bar. Y belongs to T of S1 bar means y is an adherent, adherent point. Y is an adherent point of T of S1. Don't confuse. Adherent means limit point of T of S1. Y is limit point of T of S1. If y is limit point of T of S1, then there exists a vector. Then there exists a vector y1 belongs to T of S1. Then there exists a vector y1 belongs to T of S1 satisfying the condition norm y minus y1 is less than epsilon by 2, is less than epsilon by 2. But remember, this y1 is taken from T of S1, which implies as y1 is equals to T of x1 for some x1 belongs to s1 because T is onto, because T is onto, so that it satisfies the condition norm x1 is less than 1. Again we observe from this equation number 6. I don't write equation number 6. Actually, this is not equation 1. I'm very sorry here. This is equation number 6, I think. Yes. S epsilon dash is a subset to T of S1 bar. Again from that equation number 6. Again that from equation number 6. We observe that S epsilon by 2 dash is subset to T of S1 by 2 bar. And since norm y minus y1 is less than or equals to epsilon by 2, this condition implies as y minus y1 belongs to S epsilon by 2 dash, which is subset to T of S1 by 2 bar. T of S1 by 2 bar. So similarly, there exists a constant. Similarly, there exists 1 by 2 belongs to T of S1 by 2, T of S1 by 2, satisfying the condition norm y minus y1 minus y2 is less than epsilon by 2 square, is less than epsilon by 2 square, where y2 is equals to T of x2 with the property norm x2 is less than 1 by 2. By continuing this process, by continuing this process, we obtain, by continuing this process, we obtain a sequence, we obtain a sequence xn in capital B such that norm xn is less than 1 by 2 power n minus 1, 1 by 2 power n minus 1, And also norm y minus y1 plus y2 plus and so on plus yn is less than 1 by 2 power n. Let it be equation number 7, where again this yn is equals to t of xn with the property norm xn is less than or equals to 1. If we put Sn is equals to x1 plus x2 plus and so on plus xn, then obviously it follows that norm Sn is equals to norm x1 plus norm x2 plus and so on plus norm xn. I'm very sorry. Norm Sn means you have to apply the whole norm to whole the sequence and so on. This one norm x1 plus x2 plus and so on plus xn. Let us split the norm. If you split the norm, you get norm x1 plus norm x2 plus and so on plus norm xn. Norm, this is nothing but this is less than or equals to 1. This is nothing but 1 by 2. The next term is 1 by 2 square plus and so on plus 1 by 2 power n minus 1. So this is whole less than 2. Obviously this is less than 2 by using geometric progression. Therefore we conclude that norm Sn is less than 2. For any n greater than m, norm Sn minus Sm is equals to norm xm plus 1 plus xm plus 2 plus and so on plus xn, which is less than or equals to norm xm plus 1 plus norm xm plus 2 plus and so on plus norm xn. These are simple calculations, you go through with it, which is less than or equals to 1 by 2 power m plus 1 by 2 power m plus 1 plus and so on 1 by 2 power n minus 1, which is less than 1 by 2 power m into 1 minus 1 by 2 power n minus 1. This is nothing but the sum of the geometric progression with common ratio r is equals to 1 by 2. So 1 minus 1 by 2, which is less than 1 by 2 power m minus 1 minus 1 by 2 power n minus 1. This tends to 0 as both m comma n tends to 0. What it means? Norm Sn minus Sm tends to 0 as m comma n tends to infinity. This is infinity. This tends to 0 as m comma n tends to infinity. So right, this condition shows us the sequence Sn is a Cauchy sequence. The sequence Sn is a Cauchy sequence in capital B. It is a Cauchy sequence in capital B. And what is B? B is complete. B is a Banach space, so it is complete. In every Cauchy sequence in a Banach space is convergent. This shows us limit n tends to infinity Sn is equals to x. Means the sequence Sn converges to x. This shows us norm x is equals to norm limit n tends to infinity Sn, which is equals to limit n tends to infinity norm Sn. Norm Sn is less than or equals to 2. So this is less than or equals to 2, less than 3. So you observe that norm x is less than 3. For all x belongs to S3, because of it is less than 3, I write S3. Therefore, now calculate t of x. T of x is equals to t of limit n tends to infinity Sn, which is equals to limit n tends to infinity t of Sn, which is equals to limit n tends to infinity t of Sn means y1 plus y2 plus and so on plus yn. So which is equals to y. Therefore t of x is equals to y, where norm x is less than 3. This condition applies as y belongs to t of S3. Therefore y belongs to S epsilon dash implies as y belongs to t of S3. This condition shows us S epsilon dash is subset to t of S3. S epsilon dash is subset to t of S3. So we conclude that here we conclude that here the image of the image the image of each open sphere the image of each open sphere centered centered at origin centered at origin in capital B contains an open sphere contains an open sphere centered at origin centered at origin in B dash in B dash. This completes the proof of the theorem. In the next video we learn one very important theorem which is known as open mapping theorem, and that open mapping theorem is entirely depends upon this theorem. So this is the base for the open mapping theorem, and one of the lengthiest theorem, and there is lot of derivation involved in this theorem. Keep learning, try to write the notes, then it will be more easy to understand. Keep learning. Wish you all the best.